So optics is the branch of physics which deals with the properties and phenomena of light and the effects of light. A ray is nothing but a straight line motion of light. That is, we assume light to be a particle and it is traveling in a straight line, then we can say that, okay, that is a ray of light. Now again, you have to also remember that this particular line is very close to the principal axis, right? It is very close, which means this particular angle is now actually very small. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter, that is ray optics and optical instruments. So what exactly is ray optics? What are the optical instruments and what are we going to learn will be discussed in this particular class. We have already learned the basics in your high school and I have taken this chapter in depth in the class also, but let's again keep it short, keep it to the theory, what's important. We'll discuss on that, we'll focus on that and we'll see what happens. So optics is the branch of physics which deals with the properties and phenomena of light and the effects of light. For example, if there is any reflection, refraction, diffraction, etc. like that, then optics is the branch of physics which deals with the properties, the nature, how light actually interacts and all that. Optical phenomena are studied under the branch of optics. So basically, optics deals with optical phenomena. And again, the main branch of optics is divided into two sub-branches, that is wave optics and ray optics. In wave optics, it is assumed that light travels in or light propagates in waveform. And in ray optics, we assume that, light is a particle, or simply we prove or we design. In this particular ray optics, we assume that, light is a particle, which means we are assuming, we are using corpuscular theory of light, which is an old prediction which states that, light is a particle and light cannot bend, it travels in straight lines. So that is one theory which we actually use in ray optics, but later we discovered that, light has wave nature. Through some experiments, we actually found out that, light can be a wave and it was proved to be a wave. Then we said, there is wave optics and some phenomena such as light slowing down in some mediums and all that were actually explained using wave diagrams or simply wave optics. And in ray optics, it is more of a mathematical implication. That is, it is pure geometry rather than a physical implication. We can explain many optical phenomena using ray diagram, but again, it is slightly outdated when compared to this wave optics because, again, we considered light to be a particle in this particular case. It's not wrong or anything. This was the first mode of explanation that was given to optics. Then later there was wave optics. So again, the rectilinear propagation of light just means that light is traveling in a straight line without any bends. So that is what we are going to learn in ray optics and their optical phenomena. We have already seen this in your high school lessons. The only new thing comes from wave optics. But again, we have to refresh some of these formulas and help you understand what are the important derivations from an examination standpoint of view. So again, what is a ray? A ray is nothing but a straight line motion of light. That is, we assume light to be a particle and it is traveling in a straight line, then we can say that, that is a ray of light. For example, if I take a torchlight and assume that, one photon on one particle of light is traveling in this particular direction. And we indicate that using an arrow, and that is known as one ray of light. And in all the cases, we can see that if I'm using a torchlight or anything, there will be multiple rays which is coming out of the same source. So we can say that, multiple rays together will form one beam of light. That is why when we go into traffic, we say, can you please lower your head beam or can you please dim your beam light, which means one source is projecting many light rays in one particular direction. That is known as a light beam, and one of those particular rays is known as a simple light ray. So, and what is an optical medium? The optical medium is just the medium in which light is propagating in. Maybe it is air in this particular case. Let's assume that, I'm shining my torchlight into my backyard. Then the medium is air. If I'm shining it underwater, then the medium is water. If I'm shining it through a glass medium, then the medium is glass. Now again, the next thing, what is reflection of light? Again, these are all very basic things you have already learned in your high school, but I'm just refreshing that. So again, what is reflection? When a ray of light incidents any surface, it gets reflected, right? At a particular angle, it gets reflected, and that particular ray is known as the reflected ray. The incoming ray is known as the incident ray. So basically, there are two rays. One is the incident ray, one is the reflected ray, and this is a representation of reflection on a plane surface. Again, if I draw a normal to the surface, let's say this is the normal which separates in incident ray and reflected ray, then I can say that the incident ray with the normal makes an angle that is known as the angle of incidence. The normal and the reflected ray actually makes an angle, and that is known as the angle of reflection. You all know this, it's very basic. But still, I wanted to show you or make you remember, okay, this is reflection. Because with this, we have actually formulated one law that states that, okay, angle of incidence will be equal to angle of reflection. That is, if light is incidenting at a particular angle, let's say theta, then angle of incidence will be equal to angle of reflection. These two angles will be equal to each other. That is the first law of reflection. We have the same law for refraction also, but again, let's say this is the law of reflection, and the additional statement is that the incident ray, the normal and the reflected ray all lie in the same plane. All lie in the same plane. It's not like if incident ray and reflected ray are in this plane, the normal will be in some other plane. If this is the XY plane, and it won't be like the normal will be in the Z axis, right? It'll all be in the exact same plane. So again, these are the laws of reflection, and it's basically the same thing I just explained. That is, angle of incidence is equal to angle of reflection, or simply indicated as angle of incidence is equal to angle of reflection. And again, angle of incidence, angle of reflection, and the normal all lie in the same plane, or simply incident ray, reflected ray, and the normal all lie in the same plane. These together are known as the laws of reflection. Now, since we got the obvious out of the way, let's dive into the real topics, that is the relation between R and F. So what is R? R is nothing but the radius of curvature, and F is nothing but the focus. So we all know that, and we have shown and seen and understood that in the class. What is a concave mirror? What is a convex mirror? What is a spherical mirror? What is a spherical lens? What is a plane mirror? What is a plane lens? What is a glass medium? What is an air medium? Everything was actually discussed. So you all know everything about it. So again, this will be the focus. This will be the center of curvature. This will be the principal axis which is passing through, let's say that is P, the principal axis. Then I can say that, okay, this is center of curvature. This will be the focus through which the incident ray is passing through. And this is a concave mirror. All of this is understood by itself. So let's get right into the derivation. So the first thing we are investigating is that, is there any relation between the radius of curvature of a mirror and the focus point or focal length of that particular mirror? So let's see if the radius of curvature, how much it is bent, is related to its focal length or its focus point. Is it related? So for that, we are considering that, okay, there is a ray of light. Let's say this is the incident ray. This particular incident ray is striking the curved surface at a particular angle that is made with the normal, and let's say, okay, that is retake. And let's say it makes a particular angle with retake. And let's say it makes a particular angle which is angle of incidence. Let's say that particular angle is theta. So I'm saying that, okay, this is theta. Then obviously, if incident angle is theta, then obviously angle of reflection will also be theta. So this angle will also be theta, right? Angle of incidence is equal to angle of reflection. So I can say that this will be the incident ray, this will be the reflected ray. So obviously angle of reflection will be equal to angle of incidence will be equal to angle of reflection, right? So again, we need to consider geometrical applications in this particular derivation. So we are not going to directly say that, okay, we can have any physical significance or derive some equations and say that, okay, this will be the result. We cannot actually say that. So in order to actually prove these geometrical relations, we need figures, we need Pythagorean theorems, we need triangular relations and all that. So in most of these derivations, we are going to consider these lines and shapes as triangular relations, some parallelogram relations and all that. So it's purely based on geometry. So in this particular case, the first assumption we have to understand is that the incident ray is fairly close to this particular principal axis, which means in the actual case, the ray is actually traveling very close to this particular principal axis. But the reason I have drawn it so big is that if I don't draw it so big, I cannot actually mark the individual points, the individual angles and take the assumptions. You won't be able to understand that. So in order for you to understand, I am making the figures enlarged. That's it. So in actuality, this is the ray which is passing through and hitting the curved surface. I am doing this because since this is a curved surface, I cannot take this as a straight line. But if I am using this particular line, which is really close to the principal axis, then I can say that, okay, that will be a straight line. Because when I look straight, I can see the earth to be flat. It will be straight, right? But I know for a fact that it is a curved surface. But as I zoom in, it becomes more and more flat. So that is why I am taking a ray which is very close to the principal axis. But again, in order for you to retake. But again, in order to show you that I cannot actually draw so little figures. That's why I have enlarged that particular figure and like tell you to assume that, okay, this ray is actually here and now we are going to derive this particular relation. Okay, now since the obvious things are out of the way, that is the ray is very close to the principal axis and this is the incident ray, that is the reflected retake. That is the reflected ray and this is the angle of incidence, this is the angle of reflection and both are theta. Angle I is equal to angle R, which is equal to theta, are all the obvious things we already know. Now to get into the heart of the derivation. So what do we do first? The first thing we have to do is that in order to find a relation between these two or these particular lengths, we need to consider them as triangles. Right. That is why I chose the ray to be very close to the principal axis, because then this curve doesn't matter. This curve appears to be a straight line. So then these two will be two triangles. Then I can use triangular relations in order to get the relation between these lengths. That is what I'm going to do here. But for that, I need to find out what is the angles in between these triangles. So first, I'm going to find out what is the angle NCF. So again, angle NCF will actually be equal to theta. Angle NCF will be equal to theta. Again, see, this is a straight line. This is a straight line. And if I cut a line like this is a straight line. If I cut a line like this from the center of curvature to this particular point N, that is the axis where the normal is going to be. So to that particular point N, I can say that, okay, then this angle and this angle will be same because they are alternate angles. If you remember mathematical geometry, then you know that, okay, in a parallelogram or if two parallel lines are there and a line cuts it, then the alternate angles will be equal. So since NCF is actually equal to theta, then I can say that, okay, in this particular triangle, there is theta and theta, which means this particular angle will be equal to, that is angle NFP. Angle NFP will be equal to, it's very simple. See, if this is a triangle, its interior angles will be equal to angle A plus angle B plus angle C. Then its exterior angle will be equal to sum of the two opposite angles, or it is theta plus theta or simply 2 theta. So again, it's a simple geometrical relation and we found out what is the angles inside the triangle and outside the triangle. So this will be 2 theta. Now, in order to begin the actual derivation, we are going to consider the consider the triangle NFP. We are going to take this particular triangle. Again, don't forget that this is not a curved line. This is in fact a straight line. So NP is actually a straight line. So we can say that considering triangle NFP, if I consider triangle NFP, I can say that what will be this particular side? NP. I want to know what is this particular distance. So what will be NFP? Sorry, retake. So what will be NP? NP is nothing but. So in order to find any length or any relation from this particular triangle, I am going to take the tan of that particular angle. For example, here the angle is 2 theta. So I am going to take tan of that particular angle. So tan 2 theta is actually equal to, tan is equal to opposite side by adjacent side. So this will be equal to NP by FP. So this will be equal to NP divided by FP. Let's name it as equation 1. Now again, you have to also remember that this particular line is very close to the principal axis, right? It is very close, which means this particular angle is now actually very small. So we can actually take the approximate assumption that, since 2 theta is very small, we can say that tan 2 theta will approximately equal to 2 theta, right? If I take the tan of that particular angle, since the angle is really small, I can say that tan 2 theta will approximately equal to 2 theta. And retake. So tan 2 theta becomes 2 theta. So I can write it as 2 theta is equal to NP divided by FP. FP is nothing but the distance from this particular point, the center of this particular point in the principal axis towards the focus point, or simply known as the focal length. So I can see that the distance from F to P is known as focal length, or simply the focal point, retake, simply known as the focal length. So I can see that, okay, this particular distance is nothing but focus point, or simply small f. So I can indicate it as small f. Now I have a relation 2 theta is equal to NP by F. Let's put it as equation number 2. Now again, since we have a relation in this particular triangle, now we are going to find a relation in the next triangle, that is NCP. The same thing we are going to do in the next triangle. So again, we are going to consider the triangle NCP. In that particular triangle, I can say that same thing. If I'm taking the tan of that particular angle, that is tan theta is actually equal to NP by CP, right? So tan theta is equal to NP by CP. Let's call it as equation number 3. Then I can actually say that the same assumption, since tan theta is, retake. Since theta is very small, that is, let's say theta being very small, I can say that theta approximately equal to, tan theta is approximately equal to theta, right? So taking that particular assumption, I can see that, okay, theta is now equal to NP divided by CP. CP is nothing but the distance from center of curvature to the point P in the principal axis. So again, the point from the center to this particular point on the mirror, it is known as the radius, right? It is known as the radius of curvature. How much is the radius? That is the radius of curvature. Again, for this curved mirror, this will be the radius of curvature. Or I can say that, okay, this will be the radius of curvature indicated by the letter capital R. So instead of CP, I am going to substitute R. Then I have one more relation where theta is equal to NP by R. Let's name it as equation number 4. So again, now we have two relations. The first relation is that 2 theta is equal to NP by F, where F is the focal length. And finally, we have theta is equal to NP by R, where r is the radius of curvature. Now we have these two relations here. What I'm going to do is that I'm going to take the ratio of these two, or simply I'm going to divide equation 2 by equation 4, or simply 2 theta divided by theta. So equation 2 divided by equation 4 will give us 2 theta divided by theta, which is equal to NP divided by F whole divided by NP divided by R. Right. If I do this, again you can take the reciprocal multiplication. It doesn't matter. The same results will appear. That is, NP and NP will cancel each other out. Then I can say that 2 theta divided by theta will be equal to, so 2 theta divided by theta, that is, again theta and theta cancels. So we can say that this implies 2 will be equal to R divided by F. Or simply rearranging this particular equation, I can say that 2F will be equal to R. So this is our first relation or astonishing discovery, that radius of curvature of any curved mirror will actually be equal to 2 times its radius. Will actually be equal to 2 times its focal length. So we can actually say that radius of curvature is equal to 2f. This is our first result, and this is the relation between focal length and radius of curvature. So we can simply say that take a mirror, take 2 triangles, find the tan, and since the angle is very small, we approximate it to theta, and we find the relation, we take the ratios of those two, and then we can actually say that there is a relation that 2f is equal to R. So again, now the next thing is mirror formula, and simply what a mirror formula tells us is the relation between the focal length, the properties of the image and the properties of the object. So it tells us the mathematical relation between the object, the image and the focal point, or simply the focal length. So in order to arrive at that particular equation, we use ray optics on, again, geometrical means to find a mathematical relation. So again, in this particular case also, we are going to use triangles and triangular relations. So this is comparatively a little more easier because we are going to use the theories we have already seen and uses in all the mathematics class if you are doing mensuration or simply geometrical calculations. So we have 2 triangles, that is, there is one big triangle here which is nothing but O dash P. You see this one, the object, the principal axis, and this particular ray of light together makes one big triangle, and that is known as triangle O dash P. And simply, okay, again, I hope you already know and understand that, okay, O dash is the object. So this particular object, we are assuming 2 rays of light is passing and incidenting this particular mirror. So one ray is passing through this particular point and gets reflected like this and passes through the focus point F. And then one more ray directly incidents on the principal axis and it also passes through like this. Both these rays cross over at one particular point, that will be the height of the image, and this is the object and this is the image, and the image is formed in between center of curvature and the principal point P. So all this is basics. I hope you already know this because I'm not going to focus too much on the figure and I'm going to focus a little more on the derivation part. So again, this particular triangle made by the object and that particular ray of light, that is O dash P, and the smaller triangle, that is I dash P. So I dash P are actually similar triangles. So they are actually similar triangles. So since they are similar triangles, what does that mean? Since they are similar triangles, the ratio of their sides will also be same, right? So again, since we can say that O dash P, that is this particular triangle, and the second triangle, that is I dash P, these 2 triangles are similar, we can take the ratio of their sides and the ratio of their sides will always be equal. So I can say that the ratio, that is, let's say I dash, so I dash divided by O dash, that is the length of this particular image or the height of this particular image to the height of this particular object. So we can say that I dash divided by O dash, that is the ratio of their heights, will actually be equal to the ratio of their lengths. So it will be equal to IP divided by OP, right? So ratio of their heights will be equal to IP divided by OP, the ratio of their lengths. Now I am going to name it as equation number 1. Now since this is the relation between these two triangles, that is this bigger triangle that is made by the object, this particular ray, and this particular principal axis. Similarly, image, that is the height of this particular image, this particular length, and the ray which is traveling back, the reflected ray. So since they are making these two triangles, if you observe closely, there are a bunch of other triangles here also. So in that particular triangle, I am going to take 2 more triangles. So if you observe really closely, there is one small triangle here, right? I dash F. And right opposite to that, there is one more triangle here, that is NPF. Now again, don't ask me why NP is a straight line, because again we are taking this particular ray very close to the principal axis, which means the curve is going to appear as a straight line. So simply I can say NP will be a straight line, hence these two triangles will be similar triangles. So again I can say that triangle I dash F and triangle NPF are similar triangles. So since they are similar triangles, the ratio of their sides will also be similar. So I can simply say that, okay, I dash, that is I dash is the height of this particular image, will be equal to NP. So the ratio of their sides, so I dash by NP will be equal to the ratio of their lengths. So it will be equal to IF divided by FP. So again, the ratio of their heights will be equal to ratio of their lengths. So we can name it as equation number 2. Now, is there any similarity or anything you can contribute to this particular image? So if you observe really closely, we can say that, okay, O dash is the height of the object, but that height is equal to NP, because the ray is just traveling in a straight line. It is not bending. According to ray optics, the ray of light is not bending. It is going to be rectilinear in propagation, or simply this is going to be a straight line. So this particular length and this particular length will be equal. So I can say that, okay, NP is actually equal to O dash. So I can write, this implies I can write I dash by NP as I dash by O dash, which is equal to IF divided by FP. Right, IF divided by FP. And let's name it as equation number 3. So again, we consider 2 triangles. The first triangle was made by the object, this particular ray, and the image and this particular ray. We actually formed a relation between these 2 triangles, the length of their particular sides, and then we considered 2 smaller triangles, and then we proved one more relation. We named it as equation number 3. Okay, since these 2 distances were same, we said that, okay, I dash by O dash is equal to IF by FP. Now, if I look at these 2 equations very closely, I can say that the left hand side of both the equations are same. It is I dash by O dash, which means I can actually equate these 2 equations. 3 is equal to equation number 1, or simply we can say that comparing equation 3 and equation 1, I can write, so comparing equation 1 and 3, I can write IP by OP is equal to IF divided by FP. And let's call this particular relation as equation number 4. Right, we just compared equation 1 and 3 and we got this particular relation. Now we are going to substitute the values of this particular results. Again, IP is nothing but the image distance, and since the image is on the left hand side, we use the sign convention, that is the Cartesian sign convention. So we take negative and we indicate that particular image as V. So for object we use U and for image we use V. So again, OP is nothing but the object distance which is indicated by U. And again, since that is also on the left hand side, we say, okay, we have to put a negative sign. So again, we are using Cartesian sign convention, which means anything that is falling on the left hand side above, it is going to be negative in nature. So that is why the negative signs are appearing here. And finally, what is the distance? IF. IF is nothing but, V minus F, right? It is nothing but the entire image distance in which the focus point is subtracted. So that will give us IF, right? So if that is also true, then I can substitute all these values into this particular equation. But again, since this side is also on the left hand side, I'm going to add one minus sign here also. Don't worry, it all gets cancelled out in the end, but still we have to follow the sign conventions. That is why I'm putting in the signs. Now, substituting all these results into this particular point, I can say that IP is nothing but negative V divided by OP is nothing but negative U, and the negative signs will get cancelled each other, but again, which is equal to IF, which is nothing but negative V minus F divided by FP. Again, FP is nothing but the distance from the center to the focus point, right? So we can say that is nothing but the focal length F. So that is nothing but the focal length F, and again the focal length F will be indicated by a negative sign because again it is on the left hand side. So all these negative signs will actually get cancelled each other, and we can actually say that, okay, V by U is actually equal to V minus F divided by F. So if I modify this particular equation, make it a little more pretty, I can say that, okay, V by U is actually equal to V by F minus F by F. So I just simply splitted the denominator, so I can write it as V by F divided by F by F. Or simply I can say that V divided by U is equal to V by F minus 1, right? Now again, if I divide the entire numerator by V, then I'll simply get an equation in terms of 1 by 1 by 1 by. So again, dividing throughout by V, I get 1 by U is equal to 1 by F minus 1 by V. So this is the mirror formula, or simply this is what is known as a relation between the object, the image and the focal length. So if I rearrange this particular equation, I can make it more pretty and I can just say that 1 by F is equal to 1 by U plus 1 by V. So this is known as the mirror formula. So I'll make it prettier. Since it is a standard result and you want prettier equations, I can say that, okay, I'll take the 1 by U to the left hand side. So I can say that 1 by F is equal to 1 by U plus 1 by V. So this is the standard mirror formula. So again, U is nothing but the object distance, V is nothing but the image distance, and F is nothing but the focal point. Lastly but not leastly, we'll discuss one small bit that is known as magnification. We already know what is magnification, how to find magnification and all that. But again, since it is very important in the examination standpoint of view, I'll explain what is magnification. Magnification just means how much enlarged that particular object is. For example, if you're using a lens or a mirror, you might have seen that some images may be enlarged, right? The magnification, it might be enlarged, it might be very small. If you go to certain fairs or freak shows, you can actually see creepy mirrors which make you bendy, which makes you small, which makes you stretched out, right? So all this is because of this particular magnification, and this particular magnification is indicated by the small letter m. And again, magnification is nothing but, magnification m is nothing but the ratio of height of the image to the height of the object. Generally, I can say that magnification m is equal to height of the image divided by height of the object, hi divided by ho. So this particular ratio will give you magnification, and depending on if you're using a lens or a mirror, there will be slight adjustments in the sign convention and the way we are denoting these particular terms. For example, for a mirror, we can actually say that this magnification m will be equal to negative v divided by u. The negative sign again because we are following Cartesian coordinate system, and it is one is up, one is down. So that is why we are using the negative sign here. And again, it is the ratio of height of the image to the height of the object. Again, one small trick is also there. If the image or if the magnification is actually negative, then we can actually see that. If m is negative, then we can actually say that if m is negative, that is less than 0, then we can actually say that the image formed is real. And if m is positive, that is if m is positive, if m is a positive value, then we have to say that okay, the image formed is actually virtual. So that is how we can actually find out if an image is virtual or is it real, looking at the sign of the magnification. That's a small trick. And again, if I take the magnitude values of m, then I can say that if m is actually equal to 1, then I can say that the magnification of the object is equal to magnification of the image, which means both are real, which means the actual size of the object is portrayed here as the actual image. And again, if it is greater than 1, the magnification is greater than 1, then we can say that if the modulus or the magnitude value of m is greater than 1, that means image height is more, right? If this numerator goes up, then only this magnification value will increase. Then the actual object will be smaller, right? That will be the case. And if this m value is less than 1 or the magnitude value is less than 1, then we can actually say that the object height is more and the image height is less. It's a mathematical implication. You can figure out it on your own, but still, if m is less than 1, we can say that the object will be larger. If m is more than 1, we can say that okay, the image will be larger. So again, that was a short to the spot introduction of ray optics. We'll only be focusing on the important derivations and what we require from an examination standpoint of view. So I'll see you all in the next class with a new topic. Until then, thank you.